Hello, this video is entitled Extrema of Functions of Two Variables. Alright, so we're going to be finding maximums and minimums of functions of two variables, three-dimensional functions. So it takes what you learned back in Cal 1 and expands it to a new dimension. And we'll just look at this first theorem to get us started. And this says if extreme value theorem, if f is a continuous function, variables x and y defined in a closed bound region R in the xy plane, then there's at least one point R which f takes on the minimum value, and there's at least one point R where x takes on a maximum value. That's very similar to Cal 1. If you had a function that was continuous between 2 points, you're guaranteed to have both a maximum and a minimum. Let's see. Relative extrema basically has the same idea as it would in single variable calculus. So if you're in a region R containing the point x0, y0, you have a relative minimum at x0, y0 if all the function values are greater than it in an open disk containing x0, y0, basically meaning in the immediate area. Not necessarily talking about absolute mins and maxes, but just like relative mins work, anywhere you kind of change from increasing to decreasing, or endpoints in this case too. This is considered a minimum. We have a relative maximum if if all other xy's in that area are less than or equal to your point, your function value of your point that you're saying is the relative maximum. Let's take a look at a critical point. In Cal 1 we called this a critical number, but now it's called a critical point because it's an xy point instead of just an x value. So the x0, y0 is a critical point if one of the following is true. You take the x partial at that point equal to 0, and if the y partial at that point equals to 0, you have a critical point. And then if the x partials or the y partial at that point doesn't exist, that's also similar to the second definition of critical numbers in Cal 1. I'm not sure how much we're going to encounter this in this class, but it has to be a point that contains x0, y0. Because it can get a little dicey, although this one's a pretty easy one. So I'll look at this one, and that function, you're going to have x squared plus y squared, you're taking the cube root. So that means really all real numbers would apply, all points would apply, so you could have any xy go in there would be fine. So here's the x partial, of course, bring the 1/3 down, negative 2/3, the derivative of the inside with respect to x would be 2x. So I drop this one down, and the next one, the fy, the only difference is a y. Now, 0, 0 is going to be a critical point because 0, 0 does not exist in these partial derivatives, but it would exist in the original function. So that would make it a critical point by using the second definition. Mostly we'll be using that first definition. And this theorem, also similar to single variable calculus in Cal 1, relative extrema can only occur at critical points. Back then we would have said relative extrema only occur at critical numbers. So if f has an extremum x0, y0 on an open region R, then x0, y0 is a critical point of f. So the opposite is not true. So in other words, for example, all relative extremum min or max come from critical points, but all critical points won't necessarily produce a minimum or maximum. So let's see what we have here. Here is how we're going to find these things. And we can do it, fortunately, mathematically. We don't have to worry about the graphing of these functions, but I think it's good for illustrations, I like to put maple graphs in there just so you can sort of get a visual of what we've accomplished from the math standpoint. This is the second partials test. So either, if you're using note sheets, I'm allowing you to use a note sheet, you can put this on your note sheet. Or if I'm providing formulas, so I've been known to do both, not in the same semester, but so if I was providing formulas, then I would actually give this. But either way, it shouldn't be required for you to have to memorize this in my class. I can't speak for other instructors, of course. You may have to know it. So this says we're going to set the x partial equal to 0, and we're going to set the y partial equal to 0, and then we're going to solve that algebraically. So yeah, we're going to have a system of equations. And we'll be looking for as many a, b values that we find. Those are going to be our critical points. Now, suppose you've done this process. You've set these equal. You found however many a, b's you had. And then now you're going to take each of those points and you're going to test them to determine whether they're a relative minimum or a relative maximum or what's called a saddle point. And I'll talk about that in just a moment using the graph down below. So we're going to find this quantity lowercase d. That doesn't really have any meaning to my knowledge of that's an exclusively reserved variable. I mean, I think you could put a happy face there and it wouldn't matter. But so it means we take the second partials. I remember mentioning in my video, if you watched it on partial derivatives, that we would actually be using these second partial derivatives for applications, and here they are. So if you take your point A, B, so if you have more than one critical point, you test them in any order. It doesn't matter; they're all independently tested. So if you take the second partial XX at AB, then you take YY at AB. Make that a little larger. XX at AB, YY at AB, minus the mixed partial XY of AB squared. So you come up with that number D. And then once you have that number D, here's what you do. All right, so let's see what happens. If D is greater than 0 and FXX is greater than 0, you have a relative minimum at the point AB, which you could be also then asked to find what the third coordinate is. That's only worry about if you, but that just means you would plug it back into your original function and come up with the z value. But you don't only do that if you need to. I'm just wanting to mention that. The second case is if D is positive and fxx is negative, then f has a relative maximum at that point, AB. The next case says D is less than 0. And now they see they're actually putting the z value here, which I'm not sure why, but so they went ahead and did the A, B, and then what the xy and what the z would have been. Like I said, I may ask that, I may not, but all that is just a matter of taking your A, B point and plugging it into your original function. That's all that would be. That is a saddle point. The last case is the test is inconclusive if D equals 0. Now, I try to avoid problems where it ends up being like 0, in a quiz or a test, because I want you to come up with, these first three. Most of the time, I can't think of an exception. I bet, 99.9% of the time, if the D equals 0, that probably means you don't have a min or a max. But if that was 100% true, that would have been stated in the theorem. But that's the most likely scenario, is that critical point just did not happen to produce a min or a max. Now, let's take a look at what a saddle point is. Saddle point, the name saddle comes from, the type of the position of graph, so it looks like if you put a saddle on a horse or something like that, you're sort of sitting in a saddle. But the way to think about this is, and once again, you don't have to think about it because you don't have to graph it, but I'm just trying to show you to give you a feel for what it is. It's actually a point that if you look at it in one direction, it's actually a minimum. But if you look at it, so like you look at it on the graph on the right, it's at the bottom of a curve, but that same point, if you rotate this graph around over here, it's at the top of the curve. So you see, it's not really a max, nor it's not really a min. It's almost like it's a max or a min depending on its direction. So therefore, it's a saddle point, but the saddle comes from, like I said, the way the graph that produces that makes it look like it's a saddle. So that's what we have there. So let's try this out. This sounds like it's going to be a lot of fun. This first one's a nice, easy one to start off with. I don't like for these to get too rude and too out of hand algebraically, but okay. So the idea is, you get these equations and you solve them by whatever appropriate algebra techniques you think that apply. So it's not. So this rule just kind of gets you started. Then the solving is, well, no, I'm sorry, the rule is after you solve. Excuse me. Here we're doing the fx equals 0 and the fy equals 0, and then we have to just use algebra skills, which we won't need many skills for this problem. But anyway, to kind of finagle it a little bit and come up with the points that you need, and then you apply it to the second partials test. So here's the function. I won't read all that out, but there it is. It's kind of highlighted here. Now we'll take the x partial, so 3x squared makes 6x. The y partial, the derivative derivative x, excuse me. X partial would be 1, so it's 12y, and there's no other x's there, so those would all be 0, so it's 6x plus 12y. The y partial, there's no y there. There is here, so it'd be 12x. 2y squared would be 4y. 6y would be 6. Now, back in the partial derivative, sometimes I kind of did these as a flow chart. Sometimes it's just different ways you can do this, but I just wanted to illustrate. I mean, the diagram is just there to help. It's not a mandatory thing. But what I'm trying to show you here is that to go from fx to fxx, be careful that you don't look right above, use the line that's right above you in this case. Now, had I separated these in x's and y's, and that might have been different, but I said, okay, let me just stay down this column. I'll make sure I'm careful. So I'm taking, to get to the fxx, I'm coming from the top line, not the second line. So that derivative will be 6. Now, same thing with fyy. We go back to the fy and get the y partial. That's going to be 4. And then the fxy partial, which also, remember, equals the fyx. But I did it as it's labeled. Fxy means I started with the top one, took the y partial, which is 12. Now I've got to set these two fx and fy equal to 0 and just solve algebraically. So I guess I could have moved that 6 over immediately and made it -6, but I didn't. So, I mean, you could use substitution. I thought elimination was fine here. Multiplying by -2 and then adding would get rid of the x. So you have -24y plus 4 is -20y plus 6 equals 0. Y equals 3 over 10. So that's the y value. And now you can plug it back in either equation. I chose the top one. I plugged in 3 over 10 for y. Did a little simple algebra, got -6 over 10, which is fine, but I went ahead and reduced it because in a multiple choice format, you probably would be looking at the reduced answer. But if somebody was handwriting this on an exam and they left it as -6 over 10, I mean, I would absolutely not penalize for that. Okay, now let's see what we got next. Second partials test. Now this one's kind of really easy because I started with kind of a really easy problem in the sense that, a lot of these other ones we do, you can expect when you take these second partials to have some variables in there, some x's and y's, meaning we would actually have somewhere to plug these numbers right here, but we don't because they happen just by coincidence to all be constants. So we're only testing this one point. That's the only point we have, and there's nowhere to plug them in here. So we take fxx is 6, fyy is 4, minus fxy of ab, which is 12, squared. 6 times 4 minus 12 squared is a -120. It's less than 0. And the saddle point, I wrote it this way, negative 3/5, 3/10, and then f of that. That's the same thing. I didn't actually figure it out, but I wrote it in that sort of form to where it's representing the z, or just this form right here. So we only found one critical number, and it was a saddle point. And I used Maple to graph it, so let's take a look at it. All right, so I kind of rotated it around. So you see this direction is kind of at the bottom of the arc there, but this direction is at the top, and that's what sort of makes it a saddle point. The saddle is kind of right in the middle there. Yeah. But fortunately, you don't have to check that yourself. But all right, let's get one a little more interesting here. You know, where the second partials have more variables, and I like to have more than one critical number too. That makes it more fun, so at least for me. Now this time I split these partials up. So like I said, however you write them out is totally up to you. So the last example, I went straight down one column. Here I decided to split them up as two separate, you know, you do whatever works for you. So let's check my partials real quick. So here's the function. I won't read that out, but there it is. So the x partial would be 3x squared. The derivative of x is 1, so it makes that 2y squared. 5x squared will be 10x. And then the y partial, 2xy squared. Derivative would be 4xy. 4y squared will be 8y. And then the second partial, so see that's why the x, there's the xx right below the x. So it'd be 6x and then plus 10. And the fxy, you'd be going this way, taking the y partial, only the middle term has a y, so it'll be 4y. Let's look at the y partial. Here's a y term, there's a y term. Derivative of y squared is 2y, so it makes it 4xy. 4y squared will be 8y. Let's take that part, the fyy partial then would be derivative of this, which is 4x, and then plus 8. Now they start getting a little trickier here with these equations. Most likely probably going to need some sort of substitution. You probably won't have the luxury of elimination. All right. So let's look at these equations and see what we can do. I'm going to take that bottom one and set it equal to 0. Now remember, these the solutions have to work for both these equations. So if I take this up and split this up and factor out of 4y, I have 4y times x plus 2 equals 0. So I have y equals 0 and x equals negative 2. But here is the important part. That doesn't produce, those two numbers do not produce a point. You can't make that negative 2 0 because they're both coming from the same equation. Now we might still get 0 from the other equation, but we would not have it by using these two numbers right here. That's not right. So what you do is you take these values then separately and plug it into the other equation. So for example, I'll take the y equals 0, which I know satisfies the bottom one. So let's see what x's then would also make it work. By pairing it with the other equation. So I'll put 0 in right here. I'll get 3x squared plus 10x. Factor out an x. So I have x times 3x plus 10. So I have x equals 0 and x equals negative 10 thirds that both pair with y equals 0. So there's 0, 0. And negative 10 thirds, 0. See, remember the x's won't matter in the bottom equation because if that y is 0, it's going to zero out whatever x would have been there. So there's two of them, but we're not done because now we have to see what does negative 2 work with in that top equation. So now we have to take negative 2 from the bottom, plug it into the top, and solve for the y's, y or y's plural, that go with -2 for x. So I put in -2 for x here and here, and I got 2y squared equals 8. I got y squared equals 4, and we have to be very careful because there's two answers to y squared equals 4. It's y equals positive and -2. So now we have two more points, -2, -2, and -2, +2. So actually we have 4 critical values to test for this one. Boy, that sounds like fun, doesn't it? And I just copied the second partials test. All right, so we're just taking them in, and so you have to kind of go back up. It's kind of tricky because I have to, so you're plugging them into the mixed partials. So for 0, it's going to be kind of tedious going back up here for every one of these. But when you put in 0.00, that'll be 10 for that one. That'll be 0 here, and you put 0 there, you're going to get 8. So let's scroll down, and I guess it might have been smart if I would have copied those down there. Well, I think I'll pause the video and move them down there right now. Now the mixed partials. The second partials, including the mixed partial right here in the middle. But all the second partials are now down here visible, so we can see a little bit better, because it would have been kind of tedious for me to scroll back up and keep looking at them. I mean, obviously it won't be so bad for you, when you have it kind of all written out on a piece of paper where you can look at it. Well, let's see what we have. So this one, so I mentioned it would be 0, 0, it would be 10, 8, 0. So D is positive. So when D is positive, you're going to have either a min or a max. And let's see what fxx is going to be when you put 0, 0 in there. Well, there's only one variable, the x. So you put 0 in there, so it's positive 10. So fxx, when you put 0 in there, is positive 10. So that makes it, by definition, a relative min. So when D is positive, fxx is positive, you got a relative min. -10 Put that in there for x. I got -10. For yy, plugged -10 in there. I got -16. And then the y is 0. 4y makes that 0 squared. So negative times negative. So in this one I didn't even, and which you can do this every time, is I said that this was 80 here. But if you're comfortable that it's going to be either positive or negative, you can stop. In other words, I didn't bother to write what D equaled, but I looked at it as going, hey, I got negative times negative, which is positive. I'm subtracting 0. I've got a positive value. So it's not so much that we even care about what the value of D is, other than its sign being positive or negative. So that's why I didn't show that, because there was no point. fxx in this case is negative. Here I just highlighted the fxx instead of all of them. But so D is positive, fxx is negative. We have a relative max at -10 0. All right, maybe I can shrink this down a little bit so we can see. Yeah, there we go. Now I can see everything better for these next two. Now we're testing those other two, -2, -2, and then -2, +2. Put in -2 for x, makes that -2. And put in -2 for fyy, we'll make that 0 right here. And then fxy, put in -2 there, makes that -8, but you're squaring the -8, so be careful. So the negative and negative here does not make positive. So actually it's 0 minus 64, because you're squaring the negative here. Makes that negative. And then fxx, oh no, I'm sorry, I'm saying, excuse me. fxx is meaningless. D is negative, automatic saddle point. So the next one produces basically the same numbers, except you have +8 here, but that doesn't matter because you're squaring it. So basically you have 0 minus 64, another saddle point. And there we go. We have a min, a max, and 2 saddle points. So let's take a look at this fellow here. Yeah, I should... So let's see what we have here. A min, a max, and 2 saddles. Now, I'm not going to be able to hit these at the exact right spots here, but well, there's the min, obviously. And there's the max, which you cannot see from this first view. And then I really don't have a good shot at the saddles, but the saddles are kind of right in there somewhere in that area. This, yeah, maybe this view. Actually, this view helps a little bit because the saddles would be right here. Because you see, it's the bottom part of this one, but then it's the top part of the curve that's going that way. All right. Well, like I say, fortunately, you don't have to sketch these, but so that graph kind of matches our results. There it does. You know, there are 2 saddles, a min, and a max. Like I said, that max from this view was not really visible till we rotated it, and there it is. In fact, I guess I could check the coordinates also too. Now I had to rotate the axis around, so it's kind of weird here. But the max was at -10/3, 0. So let me zoom back in on this for just a second. Then I'll move on. When I rotated the axis, that brought the negative direction towards me, which is when I did a 180-degree rotation. So that means it's -10/3, and then no direction left. So and the y is 0, and then it's straight up to here. Yeah. And then the min's right there at 0, 0, where it is right here. Yeah. All right, let's try another one. Let's see what we have here. All right, so there's the problem circled, that number 22. Usually don't see this too often. There's nothing wrong with it mathematically, but you don't really see y written before x there. It's kind of strange, but nothing wrong with it. All right, I'm going to assume that you can get the partials here without me having to run through the details. So let's look at these partials and come down here, but let's get to the solving the part I want to make sure I explain carefully. So these aren't too complicated to get these partials, so I'm going to have faith that you can do that. So now let's take my fx here, this equation, my fy, and set them equal to 0 and just kind of play around with them. Not exactly probably not helpful from your point of view other than just saying, well, I just play around with them. But really, like I said, it's, the rules are set, you say fx equals 0 and fy equals 0, but there's not necessarily a clear-cut rule to do with, because the equations can be different, sometimes linear, sometimes nonlinear. So just sort of testing your basic algebra skills here. So I took that top one and factored it out to a separate x and y. And you see I got negative 6x equals 0, and then y plus 1 equals 0. So I have a negative 6 and a plus 1. Now, just like the last problem, you do not pair these two numbers together as a solution. You take them separately and you plug them into the other equations to see what pairs up with those numbers. Now, it's possible by coincidence, like say in this example, that you might generate negative 1 by doing that, but it's not coming from here. I can promise you that. So I start with the x equals 0. It doesn't really matter which one you start with. So I put x equals 0, and then I plug it into the bottom equation, which wipes out that term that has the x. So I have 3y squared minus 6y equals 0. And factored out of 3y, so I have 3y times y minus 2 equals 0. So y equals 0, comma 2. And 0 and 2, excuse me, not I wrote it 0, comma 2. But anyway, both those y's pair up with that x. So you have 0, 0, and 0, 2. So we have those two critical points for sure. Now we plug in negative 1 to plug them into the same bottom equation right here. I put in negative 1, put in negative 1. I end up with negative 3x squared equals negative 9. After you work those numbers out and move them over, you'll get negative 9. I have x squared equals 3. So that means x equals plus and minus the square root of 3. So once again, we have 4 critical points. So plus and minus square root of 3 for x pair up with negative 1 for y. So you see I have negative root 3, negative 1, positive root 3, negative 1. So just like the last one, we have 4 critical points, excuse me. Now I'm speaking back in, like I'm in Cal 1 again here. 4 critical points. All right, this time I have the 3 partials copied right here. And so there's the 4 critical points, 0, 0, 0, 2, 3, root 3, negative 1, negative root 3, negative 1. So basically, once you get those numbers, you just kind of plug them in there. See what happens. For 0, 0, I get negative 6 times negative 6. Because both fxx and fyy will be negative 6. And $36 greater than 0. So D is positive, and then fxx is negative. So you have a relative max at 0, 0. The next one, you put in 0 and 2. So you put in 2 for y, you'll get negative 18. This one, you put in 2 for y, you'll get 6. And this will be 0 again. So you have negative 18 times 6 minus 0 squared, negative 108. But more importantly, it's just negative. D is less than 0. Saddle point at 0, 2. Now, the 2 root ones here, let's see. You put in negative 1 for this one, you'll get 0. Put in negative 1, because see, both the fxx and fyy just happen to not have x in there, so they're only y's. So that's negative 12. Square root of 3, negative 1 will give you 0 times negative 12, which is just 0, minus, and you put in square root of 3 here, minus 6 square root of 3 squared, which that will be positive. So it's a 0 minus a positive number will be negative. So you got a saddle point at root 3, negative 1. This one, Should be positive right there. And because you have negative 6x here, so it'll be positive 6 square root of 3. And you're going to get negative 108 again for this one too. So we also have a saddle point. So this one has 3 saddle points and a relative max at 0, 0. So let's take a look at the picture and see what it looks like. All right. Okay, let's scroll down here. Well, I didn't rotate this around, but there's just kind of have to imagine it's there. It's there though, but there's the max right there, and this is a saddle, and this is a saddle. Then on the other side, there would be a saddle. Yeah, if I see the one that stems off of this one, so you can't see it, but I think you imagine that it's there. So that's it. Relative max, and then 3 saddles. Very good. Let's take a look at this one. I'm going to kind of move this out of the way and put it somewhere that looks kind of confusing. This was the problem out of the textbook that I was using. I'll put it right here below it. Now the changing it, this one already has a picture, so we can sort of see what the answer is going to be as far as, maybe not numerically, but you can see visually for this one what it's going to be. But what I did on this one, the reason why I just did that, and I decided to go ahead and move it, is I went ahead and distributed through that parentheses. See, I took that negative 1/2 and moved it through the parentheses and split those up. Because that could be kind of tricky if you didn't. You're worrying about that negative sitting right there. So we're going to locate all the extrema and saddle points. But you can kind of see the answer in advance with a graph. You know, you sort of see that looks like we got 2 relative maxes and a saddle. And let's see if that's what happens. So here are the partials. Easy enough. So x partial will be 2y. And then x partial here, 4 times negative 1/2 is negative 2. And it'd be x cubed. So the fxx would just be negative 6x squared. fxy would be the derivative of this with respect to y, which would be 2. And then the y partial would be 2x minus 2y cubed, right here. And then fyy would just be negative 6y squared. So I'll take these 2 equations. I just numbered them 1 and 2 this time. I didn't do that before, but maybe it just occurred to me and say, hey, well, let's go ahead and give them numbers. You know, that's not mandatory. You should only do that if it helps you. I took the top equation and solved for y in terms of x. So you move this over, you have 2y equals 2x cubed. Therefore, y equals x cubed. And then I'm substituting that into the bottom equation, number 2. So right there. So I have 2x minus 2 times x cubed cubed, which is going to be x to the 9th, because you multiply, when you have an exponent to raise an exponent, of course, you multiply the exponents. So this looks like it's going to be big and scary with x to the 9th, but it's not, because you factor out a 2x, so you're left with a 1 here, minus x to the 8th. So you split this up, and you got 2x equals 0. It means x equals 0. Now, this 1 minus x to the 8th equals 0 gives you x to the 8th equals 1. Well, anytime that you have x raised to an even power equals 1, so that could have been x to the 50th. It wouldn't matter, because we're not trying to find the imaginary solutions. That's when it would be a mess. but we're not looking for those. But yes, this x to the 8 equals 1 does have 2 real solutions and 6 imaginaries. But anyway, anytime that you have x raised to an even power equals 1, you're going to have plus and minus 1 is going to be your answer. Because a negative 1 raised to any even power would automatically be positive 1. So we have x equals 0, x equals plus and minus 1, and you can put it into either equation. But since I already have y in terms of x right here, that would be the easiest way to do it. So I'm plugging in 0, I'm plugging in negative 1, and I'm plugging in positive 1. Now, just by the fluke of numbers in general, or whatever you want to say, math in general, this is just a coincidence that when you take the numbers 0, negative 1, and positive 1, they all cube to be the same thing. So 0 cubed is 0, negative 1 cubed is negative 1, and 1 cubed is 1. So those are my 3 critical points. Here comes the second partial test. So you put in, we're testing 0, 0 into my second, back up here to my second partial. So fxx will be 0, fyy will be 0, fxy is 2 automatically. No variable needed. No variable goes in there. So it's 0 times 0 minus 2 squared. So it's negative 4. D is negative. Therefore, we have a saddle point. Don't know why I didn't. Guess I could have put that in there. It wasn't necessary, but we can go back. It just didn't match consistently with what I'd been doing there. There we go. As you can see, it didn't change anything, of course, but. And let's see, the next one, you're going to get negative 6 and negative 6 when you put in, because here you would have negative 1 squared, which is 1 times negative 6, same thing here. Negative 6x squared, they both be negative 6. So you have negative 6 times negative 6. And then minus the 2 squared, you get positive 32, but fxx is less than 0. So d positive, fxx negative, relative max. And you're going to get the exact same thing here. And d positive, fxx negative. So as we anticipated from the early picture there, the graph, we had a saddle point and 2 relative maxes. And I just took the same thing. I decided I wanted to graph it in maple in addition to the picture that was already there. But there we go. So let's try one more of these, and that's pretty much the whole gist of the entire section is finding these problems, and in a couple of more sections we'll look at applications of finding extremum. This question is only asking for the critical points. I didn't even realize that till just now, which that's fine, but then I want to use the second partials test along with it. So we'll just pretend like it, it says use the second partials test. Yeah, I did not notice that. I guess I just assumed it just going to be doing the whole thing like we've been doing. So I copied this instruction here to now clarify a little bit that we want to do the whole thing to it here. So let's take a look at this. And partial will be 4x cubed plus 4y. The x partial, excuse me. fxx would just be 12x squared. And then fxy, we go back to the top line here to do this. So you're taking the y partial of this, which is 4. Fy is 4x plus 4y cubed. And then fyy would be 12y squared. Because it's the y partial of this, fy. So here are my fx0 and fy0 equations. Set them equal to 0, and we're solving. So once again, this is going to be similar to the last one where the substitution technique is the way to go here. So I took the top one. Yeah, very similar to the last one, in fact. It's getting the same x values again. So y equals negative x cubed. Plug it into the bottom one. 4x plus 4 times negative x cubed cubed. Now I said last problem, I might have misspoke. Let me double check. Was it the last one or was it two? No, it was the last one. I wasn't sure if it was the last one or 2 problems ago. So you factor out a 4x. So 4x times 1 minus x to the 8th gives you 4x equals 0, x equals 0. And then like I explained before about the even power, x will be plus and minus 1. Now this is a little bit different than the last one, because now y equals negative x cubed instead of just x cubed, meaning that 0 is still 0, but when you take the negative of negative 1 cubed, you'll get positive 1, and then the negative of 1 cubed is negative 1. So it's not the same 3 critical points as the last one, although it's very close. So we take 0, 0, fx will be 0, fyy will be 0, fxy is fixed constant at 4, so it's not affected by the x and the y. So it's 0 minus 4 squared, which is negative. So we have a saddle point. The next one for negative 1 and 1, let's go back up here. Put in negative 1, that'll be positive 1 when you square it. So it's 12 times 12 here, and it'll be 12 times 12 for the next one also. Because whether it's negative 1 squared or positive 1 squared, it's still 1. So it's the same 2 values. 12 minus 4 squared positive, and then the fxx is positive for both of them. So that means we have relative mins. So 2 relative mins and a saddle point. So even though algebraically that problem was very similar to the last one, it yielded completely different answers. So there's a saddle point here in the middle and 2 relative mins. You can see the downward that direction. You just kind of have to, for this part, you just sort of have to imagine it looking like this, coming down and then back up. So it's at the bottom of the graph that way, and then it's the top of the graph coming this way. And I've completely messed that up, so with that being said, this concludes the video for Extrema of functions of 2 variables.